Hello everyone, welcome to the 11th lecture. So we're kind of moving towards these more advanced topics, and today we're going to be discussing geometrical parameterization. And we actually saw that this was one of the projects, so one of the students is working on this. And during my introduction of that project I already indicated that this is quite a relevant engineering case, right? In many engineering applications we're interested in optimizing the geometry of a design, certain thicknesses, certain shapes. So we want to be able to fit that into our model order reduction framework. And to kind of put this into context in where we are at right now. So we've done all the fundamentals, we have talked about all the basic reduced basis methods, except for the 7th one. And then last time what we did was we talked about this non-affine parameter dependence and how we can still fit that into the model reduction framework. And we saw that we had this empirical interpolation, either the discrete empirical interpolation or the non-discrete empirical interpolation method. And we'll actually see that that also shows up for our use case right now, the geometrical parametrization. Yeah, so this is the three to last lecture. Okay, I'm going to jump right into my notes, and I have some more slides later as an example case, but I want to talk about the theory first. So what is it that we exactly want to do, right? We're talking about parameterized partial differential equations. I don't know why I changed to blue, there we go. And the way that we talked about those before was in the following form. So we have partial differential equation as a statement, and I'll focus on our core example of heat diffusion, where we have some sort of diffusion coefficient, which may be parameter dependent, right? That might be a variable in our engineering setup, in our optimization problem, or in our multiscale problem. And we're trying to solve for our solution U. And we might also have forcing on the right hand side. For the example that I want to focus on today, I'll actually set this one to 0. And this PDE is set in some sort of domain omega. Now we don't only have this partial differential equation, we always also have a couple of boundary conditions that come with that. For instance, a Dirichlet condition, which will also set to 0. And maybe a Neumann condition, and in the current framework that will be this. I'll set that guy to G of n, for instance. And what I actually want to illustrate today is the case where this guy might also be orthotropic. Yeah? So we might have a diffusion coefficient that is not isotropic, in the sense that it does have a difference in terms of how well it allows heat to travel in certain directions. So what might that look like? Well, we could for instance look at a heat fan. Right? So if you open up a computer, you'll find that on all the heat generating components there are these sort of brackets on there that are connected to, for instance, the processor, right? So there's heat coming in from the bottom, and this has to somehow be designed in such a way that it allows as much heat to dissipate out as possible. And in a design like this, we could have different materials. Maybe we want to have a different material for the base than for each of those fans. So we could have a different D over here, and a different one over here in each of the fans. And maybe our fan is made up of layers so that heat is transported upwards as soon as possible, so then this guy would actually become orthotropic, right? And just for the sake of completion, I also write this as an orthotropic parameter. So we would have a D1 and a D2, and this might be dependent on our parameter point in our search space, right? So these are variables in our partial differential equation. And also these different heat influxes and outfluxes might also be parameter dependent. Yeah? So I'll make this into a mu as well. Now this is sort of the case that we've looked at before, right? We've looked at being able to handle a variable coefficient in our PDE, and we've also looked at variable loads, because in the anti-boundary conditions also show up as a right-hand side forcing. So that's what we're familiar with. And we're even familiar with at this point if these parameters become spatially dependent, right? That's exactly what we talked about last time. So what changes now? Well, the thing that we're going to vary right now is exactly this domain omega, which means that also all of our boundaries change. And in our design optimization, that might actually look like we might want to change the parameters of these flanges such that they become very thin and long, or maybe the middle one is still a little thicker, and only the outer ones would be very thin. And I might be interested in the rate at which we can dissipate heat with a design like this. So now the new parameters in our parameterized partial differential equation might, for instance, be the height and the width of these flanges. Yeah? So that did not yet immediately fit into the framework that we talked about previously, because now our domain changes. And that's actually a little bit of a funny context, because we typically, the way that we set up our problem in a finite element sense is that we look for solutions in these Hilbert spaces, right? We look for a solution U in H1, and H1 is set on omega. And now what we're doing is we're changing omega, so we're actually changing the space in which we look for our solutions. So conceptually or mathematically it's a little tricky. Now how does that show up in our weak formulation? Remember that the way that we obtain our weak formulation from this guy is we multiply by a test function, integrate over the domain, and do integration with parts, and we would get now an integral of, and the nice thing about the way that this problem is set is that this tensor actually pulls out up front, yeah, so this works quite nicely. That means that we get a boundary term, but the boundary term we have a condition for that, so that one moves to the right hand side. We have now, normally we would have here d mu gradient u dot n times v, and well, this guy is equal to g n of mu minus. So that's the way that we normally work with these parameter dependence in our PDEs. And right now what happens is that also the integral itself becomes mu dependent. And this is really a bit of a tricky situation. We're looking for solutions in different Hilbert spaces. Well, that might still sound a little bit abstract. To make it a little bit more concrete, what we might naturally consider doing is that we would remesh for every different parameter point. Well, that would still be a very expensive procedure, and that's typically not what we want to do, but conceptually that's something that we might consider. And then we already realize, well, remeshing everything doesn't really fit into the framework that we've built so far, because now we have our solution vectors represent completely different nodes in a different mesh, right? So we can't put them all in the same snapshot matrix, for instance. And if we build our affine decomposition of our stiffness matrix, then every row and column corresponds to a certain node. And if we have a different mesh for each case, then we also cannot use our affine decomposition anymore. So that all doesn't work. So what we're going to do instead, and this is actually something that we should find relatively natural right now, is we're going to map our true configuration, which is parameter dependent, back to a reference configuration. And we're going to work exclusively on that reference configuration. Yeah, so we mesh our reference configuration, we define our solutions on that space, the Hilbert space remain constants for all choices of parameters, or remain the same spaces. And we somehow have to change our partial differential equation such that, well, what I wrote in red over there is actually removed. Yeah, so we stick with the same setup that we had before, the same constant domains, and somehow this parameter change should show up in the equations themselves via sort of a mapping. So what we're going to do is we're going to define a reference domain. I suppose that we're working with a simple example of a cube. And I'll denote that with a hat. And then our parameters define some sort of change of volume, change of domain. So this is now our omega mu, right? So this is really the true case. That's where the partial differential equation is set in a parameterized sense. And now we need to define some sort of mapping. So you want to be able to say for every point in our reference domain, what is now the corresponding point in this true domain. Yeah, so I'm drawing this for the corners, but I should be able to do this for every point in this domain. Yeah, so also central points. So this is the reference. Reference domain, and this is the true domain. And this true domain, the shape of this true domain is parameter dependent. And now we want to have a mapping that maps from omega hat, our reference domain, to our true domain omega mu. And we'll call this mapping T. And clearly, because the true domain depends on the parameter, also our mapping depends on this parameter mu. So now our nomenclature will be that we have points x with hats that live in our reference domain, omega hat, and we have our regular coordinate x that lives in omega mu. And these are vectors. Yeah, points are vectors. So what can we do with this mapping T? Let me actually talk a little bit about this. So normally, this might actually be something that you've seen a couple of times. In continuum mechanics, this is the core framework that we use to describe all kinds of kinematic relations. Also for finite element methods, nonlinear finite element methods, where we have these nonlinear deformations or geometrical nonlinearities, we're also always mapping back this true configuration to a reference configuration. And even for the simplest case of linear finite elements, we also have these reference elements that we map to the true elements in our mesh, right? So we should be relatively comfortable with this concept of taking a reference domain and taking a true domain and having a mapping between them. Now, in all the cases that I just summarized, we actually have a relatively fixed mapping. There's really one mapping that maps every point from our reference to our true domain. That's exactly what defines the kinematic deformation. In our case, we're a little bit more flexible because in the end, all we really want to describe is this omega mu, and the way that is mapped to this artificial reference domain is relatively arbitrary, right? So really the only things that we kind of want is that points align in the way that they should, right? So that certain boundary points here are also in the same order over here. But other than that, we're extremely flexible in our choice of mapping. We just want really our boundaries to be boundaries in this true domain as well, and anything else, well, it doesn't really matter too much. So we're quite flexible. And in particular, that means that we'll pretty much always be able to find a mapping that is invertible, yeah? So we can go back and forth. So what can we do with these mappings once we have obtained this T? So from this T, which we assume to be invertible, and also smooth. And that's kind of what I hinted at a second ago, that, well, because we're so free in our choice, we can typically find a T that satisfies this. We know, well, first of all, what we know is we can take a point in our reference domain, and we know what the corresponding point in our true domain is. Yeah, so we can say that the function, the true domain location x, then becomes a function of our reference domain location x hat. And the way that we would obtain this guy is as simply the transformation T, which is mu dependent of x. Now, which means that T is also a vector valued function. Yeah, so this is saying, give me a point in our reference domain and I'll be able to give you the point in our true domain with this mapping. Now I can also do the opposite. I can say that actually my reference coordinate x hat is a function of x as the inverse of this mapping. Yeah, so give me a point in our true domain, and by inverting t I'll be able to say what reference point or what point in the reference domain corresponds to that. Yeah, so I have mappings back and forth. So with that notation and with that knowledge, what happens to our example partial differential equation? And I'll actually simplify this example a little bit. I'll actually simply use a diffusion or a heat diffusion coefficient that is actually isotropic again. And we'll see later towards the end of this lecture why I chose to introduce it as orthotropic here. Yeah, but for now I'm going to choose that this d is simply equal to, so consider the previous example. With d of mu simply being some sort of kappa times the identity. Yeah, so this is an orthotropic tensor again. And this kappa would now also be our parameter dependent diffusion. So with that choice and with this nomenclature, what does our differential equation in weak form look like? Well, we have an integral over our true domain, omega mu. We have this kappa, and let me actually drop the subscript mu there. I don't want to confuse, I don't want to have too many subscripts in my notation. And I'll use this now in index notation. So what is the gradient in index notation? Well, it's a vector, so that leaves an open index. I'm doing a dot product. So we're summing over the index I of partial xi of u times partial xi of v. And remember, in index notation, the way that we do that is that multiplication of repeating indices is a summation. That's Einstein notation. And we have now also this this differential volume, d omega, which is a volume measured in our true domain. And the thing that I emphasized a second ago is that these functions u and v, well, they are members of this Hilbert space, H1, right? Functions that we can take one derivative of without it giving infinite values. And H1 specifically also on this domain omega mu. And if I want to change this somehow into a differential equation that is set on a reference domain, well, that's kind of the first thing that I have to tackle. I want to be able to use a function u that is not defined on omega mu, but on omega hat, a reference domain. So that's the first thing we're going to do. So first, we define a new solution, u hat, which is a reference solution, which lives in, well, again, H1, but now on omega hat, our reference domain. And we're going to define this guy as, well, it is a function of points in that reference domain, right? So it's a function of x hat. And we also know that we can, with our mappings here, we can say that this guy, x hat itself, is a function of x, right? Which means that by just a substitution of this mapping, we can say that u hat is actually also a function of x, which lives in our true domain. And that function we want to be equal to u of x. Yeah, so this might seem almost trivial, but what this means is that u hat is we call this a pullback of u. So give me a function u in our true domain, and I'll be able to give you a corresponding pulled back solution in our reference domain, simply by the substitution of transformation of coordinates. But still, this is the function that I'll be working with in my weak formulation. Now let me first substitute that guy. So I still use my integration over omega mu, right? So we're continuing here, which means that I'm evaluating everything for points set in omega mu, which means that even though I want to use u hat, I still want to be able to feed u hat points x rather than points x hat, which means that I'll use this formulation right now. And this is still perfectly well defined. Even though I'm using these pullback equations, I can still feed them points relevant to this integral in omega mu via this substitution. And we still have our differential volume associated with that, which is also still in our true domain. So now we're sort of at a point where we can start changing all our occurrences of x with occurrences x hat and changing everything into integrations on our reference domain. So that's what I'll do now. I'll say this is completely equivalent, or equivalently, we'll have an integral on our reference domain of kappa. Now we have to use the chain rule, or we can use the chain rule, let me say it like that, whereby rather than taking the partial derivative of u hat with respect to x, I will now take the partial derivative of u hat with respect to x hat, right? That's the proper the proper operation on u hat in this reference domain. If I use the chain rule, and that means that I still get partial x hat over partial xi. Yeah, but this is something that I'm happy with. I can write this as a gradient set in my reference domain. Now I can do the same thing for the test function. So this should be j, and this should also be j. Now this is a summation. Let me be a bit more specific about the fact that all of these guys are vectors. I think the rest was fine. Yeah. So here also we're doing the chain rule. And the next thing that I want to do is, since I'm integrating on my reference domain, I also want to take into account, in the end, what the integral needs is this differential volume in the reference domain. But of course there is something still wrong there, right? Because if we take, for instance, a nice square as a volume in our reference domain, yeah, then this being our reference domain, or our differential reference domain, then if we would map this guy to the true configuration, then this guy might become very skew, right? It might actually look like something like this in the true domain. So this would be the corresponding differential volume in the true domain. So we have to take this into account. Well, there's a change of scaling here. Taking a little integral, a little differential volume in my reference domain might actually count for much more volume in that deformed configuration, the true configuration. Yeah, so for now I'll just write this as sort of a ratio as d omega mu by d omega hat. And I think you guys should probably already be familiar with that, what that is. That's actually going to be the determinant of that mapping. Yeah, I'll see that in a second. But this is where that comes from. So what I'm going to do next is, well, I already kind of mentioned this, the determinant of the Jacobian, or the determinant of the mapping, well, the mapping, or the determinant of the gradient of the mapping actually. And the gradient of the mapping is what we call the Jacobian. So what I'm going to do is I'm going to define this tensor, which we call the Jacobian, and I define this as my derivative of the mapping T, which was a vector, so I'm taking the ith index with respect to a reference coordinate and an xj. So that's how we define a new tensor, which we call the Jacobian. Now we can do something similar for the inverse of the mapping, right? So because, just to be clear, remember that partial t, partial x, well, what was t as a function of x? That was precisely this x hat, right? Oh, sorry, am I saying that right? Yeah, no, t as a function of x hat, sorry, is going to give you x. So this is really nothing more than partial x over partial x hat. What I need, however, is quite the opposite of that. I need to have a partial x hat over partial x. And that ends up actually being the same thing as t inverse partial x j, which is the inverse of the Jacobian ij. And this is actually what we recognize from our equation. And here and here. Yeah, this is partial x hat with respect to x, and that's precisely what this mapping was, right? So this is going to be the inverse Jacobian and the ijth component of that tensor that matrix. Now the gradient of that mapping is saying something about how things are stretched and compressed, and what we know from our Affine element classes is that precisely that ratio of volumes is going to be the determinant of the Jacobian. Yeah, so that's why we always have, and also in the example code that you have in Matlab, you have this, I define the Jacobian to be h, I believe, and then in the Affine element, or the element routine, you still have this multiplication, or the division by j of the derivatives, that's precisely that. And then in the integral routine, you have a multiplication by, well, j squared, because for simple cases, it's simply going to, the determinant is just going to be sort of a sum square. Okay, but this is more general, right? This does not take into account squares that are stretched into new squares. This could be any kind of mapping, right? From in this case, from sort of a rectangle into sort of a potato shape. It could be anything. Okay, so this was the index notation. Let's go back to vector notation. I always find that a little bit more pleasing to read. So we have now our integral on omega hat. We still have a kappa. Then, well, this set of index notations is really just a matrix vector multiplication, where the matrix is this inverse Jacobian, and the vector is this gradient of u hat, but not really just a gradient, right? Let me also emphasize this is the gradient in reference coordinates. Yeah, so I'm writing this as a gradient hat. These are partial derivatives with respect to that x hat coordinate. So this is going to give you a vector, and I dot that with, well, this is pretty much the same statement. J inverse of gradient hat v hat. Now we have the determinant of j as the scaling of volumes, and then we're allowed to integrate in our reference domain. Now, our mapping is parameter dependent, right? The shape of this true domain, and thereby also the t, will be dependent on our choice of parameters, right? The widths with which we have scaled things, or the heights that we have stretched out. So that's going to show up in the end here as this mu dependence of our Jacobian. So I'll fetch that back in there. So in a general sense, the Jacobian will be dependent on a parameter, but also on space, right? Typically, if we have this funny stretching into a potato shape, then we won't find a mapping that maps every point in a straight sense. So the mapping is going to change per point in a reference domain. So j is now a function of space and of this parameter. Okay, so this is already looking sort of okay, but we can write this even nicer. Let me propose the following rewrite of these matrix vector multiplications, because that's in the end all this is, right? All this is a matrix multiplied by a vector, matrix vector, dotted with another matrix, which is actually the same matrix times a new vector. Yeah, so let me quickly introduce B as this gradient of U, and C as this gradient of V. I just want to show you how you can reshuffle this into something nice here. So a dot product, you can actually write that as transposing either one of the vectors and putting that up front. So that is the same thing as taking AC transpose and doing a vector-vector multiplication with A, B, which is the same thing as C transpose A, transpose, that's the way that the transpose carries over, A, B. Now I can recollect this a little differently, and now we again recognize that this is really just a dot product between these guys. So I'm going to do the opposite operation here, and we find that this is the same thing as AT, A, B, dotted with C. So what does that give me? That means that this integral statement is equivalent to saying, and I'll actually skip ahead, a new, completely new diffusion tensor, which is mu dependent times the gradient of U hat dotted with the gradient of V hat, the omega hat, with D is equal to, well, first of all, kappa, then A transpose was J inverse transpose times J inverse times determinant of J. This is a scalar. Well, we also define this guy to be a scalar. These are both second order tensors, so this is going to be a second order tensor. And given how our Jacobian, well, it can be any kind of non-isotropic tensor, that means that this the new diffusion coefficient, this equivalent diffusion coefficient, is going to be some sort of orthotropic tensor. Yeah? And this is precisely kind of what I started off with without these mu's, right? We set a partial differential equation on a fixed domain, and we had our parameters only in the equations here on the left. Yeah, so, and that's what we have been doing so far, that's what we're familiar with. And that's precisely what we get if we use these mappings to map everything back to a reference configuration. Then we again have a set of partial differential equations, a set now on a fixed domain, omega hat, where we have now this parameter dependence sort of in these parameters, in this case as an orthotropic diffusion. Yeah, so that's the result that we obtain by using these mappings back to a reference configuration. So that means that in principle we can do everything that we are already familiar with in a model reduction framework. Now specifically, if our Jacobians, which are mu dependent, is also a function of space, well then we would need to do some one of the methods that we talked about before, with this empirical interpolation. Yeah, to obtain that the bilinear form that we're working with, mu v, can be written as this, that is then an approximation, as this affine decomposition of a finite set of parameter dependent functions theta multiplied by parameter independent function bilinear forms BQ. Yeah, so that last parameter dependence and the spatial dependence is purely in this new sort of artificial diffusion. And then with the empirical interpolation we can separate that into a finite sum of components. Okay. So that is if our Jacobian is dependent on x. And I've been saying, well, that might generally be the case. But it's not always the case, and there's actually a whole range of practically relevant cases where that is not the case. So let's consider that as a particular example, because of course that's the nicest application. And then we'll find that we don't need this empirical interpolation, and this can really actually be written simply as a sum over a couple of components. So when is our Jacobian actually independent? Of x. And if I want to be careful, I should actually also say that this is the reference x, right? Yeah. Well, remember J was the sort of derivatives of the mapping. So when is the derivative of a mapping or of any function constant? Well, that's if it's somehow a linear mapping, right? And more specifically, if it's an affine mapping. So the general case where that is independent is if our mapping T, which is a vector valued function of mu, which takes a point in our our reference location. If we can write that as G mu times x plus b. Yeah, because if that is the case, then our Jacobian, which is, let me rehearse that is actually simply the derivative of our mapping T with respect to our point x. And we can already immediately see this is going to be equal to that G matrix. Now this is what we call an affine mapping. And maybe it's useful to at this point rehearse what affinity actually is, because I've been talking about this affine decomposition all the time. So affinity is just an extension of, well, linearity. So this function would be linear if you did not have a b. Remember, linear means that if you add a and b as an argument, then the result will be the same thing as the operation on a plus the operation on b. Which is not the case if you have this offset, this b. So an affine mapping is just a linear mapping with a transformation. Now what that means geometrically is that all straight lines remain straight. They may tilt, they may rotate, they may stretch, but all straight lines under this mapping remain straight. Yeah, so an example of that would be, for instance, changing a cube into sort of a tilted, well, for instance, something like that. Yeah? This would be an affine mapping. Because any line here that was straight is still going to be straight here. And also over the diagonal, every straight line will remain straight. So what kind of mappings or what kind of components can a mapping like that have? Well, it can involve rotations, as you're seeing. Rotations. It can involve stretchings. As you can see, we can also just move the whole thing, right? So it can also involve translation. So that's still a relatively broad class of operations that work nicely and have a constant in space, Jacobian. Yeah, so again, looking back at the example that we discussed before, with this heat, these flanges, changing widths and heights, those are affine mappings. So that's exactly what we can do. So the example from before, Let me take one piece of that. So yeah, we had this rack, right? So let me take one flange of this. So one section. Where as parameters we had this diffusivity in the base, and diffusivity at the flange. There might be different materials, but now we can also add this height and this width as a parameter, yeah, so that we could obtain, for instance, something that looks like that. And that falls in our classification now. So this is an affine mapping, but not an affine mapping of the complete geometry, right? So we're only affinely mapping a section of it. So that's something we have to take into account. In a global setting, this is not an affine mapping. It's only an affine mapping of a subdomain. So in order to make this fit into this framework, but without the need for an empirical interpolation method, we need our Jacobians to be, well, at least constant piecewise on each domain, which means that if we want to do something like this, we first have to separate things into individual domains that each map affinely. So we're going to subdivide our geometry into parts that are affinely mapped. So we begin, let's call this our reference configuration. And now we want to divide this into pieces such that that mapping is sort of an affine mapping. Well, the most straightforward thought might be to do something like this. Right? So we define an omega 1 and an omega 2. And then, well, omega 1 remains the same, right? We're not changing the dimensions there. And omega 2 would be affinely mapped. So in principle, this would be a subdivision of domains that are affinely mapped, and still this is not something that I'm happy with. And the reason why I'm not happy with that is that this mapping doesn't coincide from these two domains. I want this mapping to be smooth. Yeah, that's one of the assumptions that we made here. One of the things that we said about T is that it's smooth. And clearly if I have a different mapping in one domain that does not match with the other domain, then it's not a smooth mapping. And that's important to just clarify that. That's important because we're taking well derivatives of these mappings, right? And across that interface, the derivative would not be well defined. So the reason is along that interface, T is not smooth. Yeah, so that's why we're not happy with that. So now let's do that differently then. The obvious alternative choice would be to just make the cut like this and define omega 1 here and omega 2 here. Is this now an affine mapping? Well, actually not, because if I change my height and I want this to be smooth, then this guy needs to stay at the same location, which means that everything in this little square would somehow have to remain stationary while the rest gets stretched out, which means that, well, any line that would kind of lie straight on across this interface would end up being something that kind of looks like this. Yeah, it would be stretched upwards and would not be stretched in the bottom. So again, this is also not something we're happy with, because this is actually not affine. As we can see from this straight lines not remaining straight. Which means that we really cannot do this subdivision with only two domains. The answer is going to be we're going to have to divide this into three domains, where we have an omega 1, an omega 2, and an omega 3. And this actually also fits kind of nicely with our change in different material coefficients, because now we have one constant material coefficient in each, constant yet parameter dependent, material coefficients in each subdomain. Yeah, so this is good. Yeah, just to clarify this a little bit more, the mapping. Let me write that in a more general statement. So the mapping, even though we divide the geometry in subsections, the mapping needs to match from omega I to omega j for all possible choices of omega I and j. Yeah? So that was not the case here. So that's the one thing that we kind of have to think about once we do a subdivision like that. Which means that sometimes you end up with pretty funny looking stretches and subdivisions in order to make everything map affine. Yes? And if you do that, then you can actually get pretty far with just affine mappings. So what does our bilinear form now look like? Bu, v, parameter dependent. Oh, clearly we're going to integrate now over each of these separate volumes. So you have an integral over omega I, or omega 1, where we have our diffusion kappa 1 is what we had there, right? We have kappa 1 at the base. Times simply the gradient of u dotted with the gradient of v. And I'll actually drop my notation with the hats from now on, because I'm going to assume that everything is now set on this reference domain. That's the domain that we're working with. That's what I'm calling completely omega. Yeah, so omega without the mu and without the hat now refers to our reference domain. So that guy was simple. There's no stretching involved. We have omega 2, but the second material parameter. And now we have this stretching involved there, right? So I'm just going to call this D2 for now. And we'll see in a second what exactly is inside D2. Gradient u with gradient v. And we have the third integral over this volume, well, it's still on the base, so our material parameter was kappa 1. We have also a D3 here, which involves the stretching in that domain. So what do these new artificial diffusion tensors involve? So let's take a look at our mappings and our Jacobians in each of these situations. So let's take as example first G2. Right? So this is an omega 2. So we have an affine mapping in omega 2, which means that our mapping looks like this, which means that, well, we're interested in the Jacobian of the mapping, so all we're interested in is G. So what is G for this mapping? Well, we have a stretching in X and we have a stretching in Y. Let me call this the reference domain, and I'll use reference values W hat and H hat. So if I stretch my domain to omega 2, this flange, in X, so I'm going to take an arrow here that is purely along the X-axis with a width of W hat, then the result in the end is going to be W. Similarly, if I have an arrow purely in the Y direction of a magnitude H hat, then the final result is going to be H. After we multiply the vector by this G, right? If we do the mapping as a matrix multiplication times X, then my example X, which would be this arrow, should map to the small arrow, and this arrow should map to the long arrow. So that is simply a matrix that is diagonal and has zero, or is symmetric and has zero offset values, which means that it's diagonal. So the first guy is the stretching in X, while the stretching ratio is going to be, well, it's going to stretch from W hat to W. So the ratio is going to be W over W hat. Now if I operate this on a vector that lies in X, let me quickly draw that. A vector that lies in X, so the Y is 0, and I have a width of W hat, right? So I have a vector lying like that. Then the output will be a vector with W. Yeah, that's this guy. So that's what we expect, that's what we want. Well, the same argument also holds for the other diagonal component, and we get H over H hat. Yeah, so this is our G matrix that defines our affine decomposition, or our affine mapping, sorry. And that is also immediately our Jacobian, right? Because the derivative or the gradient of our mapping was G. That means that D, and specifically D2, was equal to the determinant of this mapping. What's the determinant of this mapping? That is this component multiplied by that component minus this component multiplied by that component. So the determinant of G is simply WH divided by W hat H hat. Does that actually make sense? Do we expect the determinant of our mapping to be like this? Yes, we do, because we said that the determinant of J was precisely defined as this ratio of volumes, right? The volume in the true domain over the volume in the reference domain. Well, that's precisely what we're seeing here, right? This is a volume in our true domain, this is a volume in our reference domain, so that's exactly what our Jacobian is doing, as anticipated. Then we multiplied that by J inverse transpose, and we multiplied that by J inverse. Well, so first of all, this is a symmetric matrix, so transpose is equal to the matrix itself. Then an inverse of a diagonal matrix is going to be the inverse of the components along the diagonal. Yeah? So if I take the inverse of this matrix multiplied by the inverse transpose, then that's nothing more than W hat square over W square and H hat square over H square. Which means that the final matrix that I end up with as my orthotropic diffusion tensor, artificial due to geometrical deformation, will be W hat H over W H hat and W H hat over W hat H. Yeah, so we get different components in our XX and in our YY, and that kind of makes sense, right? If we change our true configuration by stretching out that flange, but we want to somehow compute that on a reference configuration where the flange is not stretched, well, it means that effectively what's going on in that reference configuration is that we have a smaller diffusivity in that length direction. And that's exactly what that orthotropy is taking into account. Now let's do the same thing for our G3. That was that square in the left bottom. So this guy does not stretch in the y direction. Any vector along this edge remains the same. It only stretches in x direction. So we get, on the x direction we get the same one, W over W hat. The off diagonals are still 0, and the YY component is 1. Yeah, and then if we go over the same process, then D3 is going to be equal to W hat over W and W over W hat. You can work this out yourself if you're interested. And as you can see, these guys will be parameter dependent because these W's and these H's, the new configuration, the true configuration, is parameter dependent. Those are our parameters. So these D's showing up in a bilinear form over there and over there, they are parameter dependent, and the kappas are parameter dependent. But after that, we have set ourselves in a reference reference domain, so that doesn't change. And even right now with this setup, all of these components are spatially independent. Yeah? So this is already an affine decomposition of our partial differential equation. Okay, I think in terms of theory, that's all I wanted to discuss. So I've seen the general theory of geometrical parameterization in terms of the arbitrary mapping, where we see that the Jacobian kind of shows in as sort of a material parameter if we set everything in a reference domain. Then normally we would have to use empirical interpolation to tackle that. For particular mappings, we don't even have to do that. If it's affinely mapped, then everything falls into place quite nicely, and we can use all our previous theory. So how well does this work? I have some examples here. So this is an example also from one of the books that we've been referencing also in the introduction as our literature, our reference literature. So this is precisely sort of the example that I've also been working with in the theory. So we have sort of a thermal fin, is what they're calling it. We have two materials. So we have a kappa 1 and a kappa 2. And I think as a parameter they used also the height of this fin. So that's another parameter. And they also used as a parameter not immediately the heat influx or outflux, but they used also a material parameter that kind of models how effectively heat is dissipated. Yeah? So if this is submerged in water, it will behave different compared to if it's submerged in air. So they have another heat dissipation parameter. So this is the reference configuration, and they have a mesh, so they compute everything on here. And now you can see that I think they used the greedy method for this. So I think this is their error estimate. And they can see how the error drops with the number of bases. Yeah, that's what this is showing. And this is probably a relative error, so you can already see that, well, after they use 16 modes, they're below a 1% error. So what are examples of modes that they obtain with greedy method? Well, those are these guys, yeah? And this is now mapped back to the true configuration, the true domain, just to see what they look like. In reality, the way that they would compute any of these would be in that reference domain, yeah? So in this configuration. But of course, since we're using a greedy method, we know which parameter point each of our bases corresponds to, and the parameter point defines that new true configuration. We can actually map this in this true configuration. Now, just as an example, they're using these bases now to solve a model-order reduced version of the problem for a particular parameter point. I'm not sure what kind of point they chose, but here you see what the real solution is. So this is the real solution. This is the model-order reduced solution, and this is the error. Yeah? So we see some peak errors, right? The maximum errors, well, they're clearly in the range where things behave a little funny, namely along the edge. Such sharp corners are always a little tricky, but that's still of the order of E minus 5. And so it's really a very effective model reduction technique, despite the relative complexity of using parameter-dependent geometry. Okay, that's everything I had for today. Thank you for your attention. So this was there's going to be 2 more lectures, both more advanced topics. Next time we'll talk about nonlinear problems, and after that about one last model reduction technique, namely proper generalized decomposition. Yeah, so I'm looking forward to seeing you there.